In the early 1980s, Ethernet was but one of many budding networking technologies, all vying to become the standard. And that's when a group of engineers in Maynard, Massachusetts set about creating a device and a protocol that would shape networking for decades to come. Today on the Serial Port, we're looking at the DEC LAN Bridge 100, the world's first Ethernet bridge, as well as Radio Perlman's spanning tree protocol, both of which helped Ethernet break free of its limitations and become king of the local area network. The first version of Ethernet has its roots all the way back in 1973 at Xerox's Palo Alto Research Center, or PARC. That's where Bob Metcalf and David Boggs designed the first Ethernet protocol that ran at 2.94 megabits per second to network Xerox Alto computers. However, in 1976, with the help of his colleagues, the speed increased to 10 megabits per second. Metcalf then formed 3Com in 1979 and brokered a deal between Digital Equipment Corporation, Intel, and Xerox to form the DIX Alliance that would help propel Ethernet into the marketplace. But this is probably not the Ethernet that you're thinking of. Let's just say that things were a bit different back then. These early versions of Ethernet used a large diameter coaxial cable as the physical medium for data transmission. The cable, which was made by Belden, was nearly a half-inch in diameter, made up of a center 12-gauge copper conductor, which was surrounded by thick polyethylene insulation, and then both an inner and outer shield to protect against electromagnetic interference, and all of which was encased by a PVC jacket. This resulted in a stiff, difficult-to-bend cable that became affectionately known as Thicknet. And installing this stuff was no joke. Ethernet during this era was primarily used in environments like factories and campuses, not in offices or homes. We spoke to John Reed, who was a field service technician at DEC for over 40 years starting in 1980. He recalled just what it was like installing Thicknet.
I started work at Digital in 1980. And worked there through the rest of my career. I retired after 40 years. Of course, it didn't have the same logo on my paychecks. Digital was bought by Compaq. Compaq was then bought by Hewlett-Packard. I've had a lot of different titles on my paycheck, but I worked for the same group of people. So I started in the factories in 1980 building the VAX 11780, which was one of the first really commercially viable mini computers that took off wildly in college campuses.
But DEC then moved the manufacturing of the 11780 to Puerto Rico, and Reed made the decision to go into customer service and repair to be able to stay in the continental U.S.
So I started on the VAX because that's what I knew. I was an expert at it. At the chip level, I knew every single chip on the 11780. But most of the problems were in interconnecting computers. I had a natural penchant for this interconnecting thing, so I started working more towards the networking. This is a roll of 10 base 5 cable. It's thick and heavy. It's the size of a finger. So this cable we put in the ceilings of buildings. This right here is a PVC cable, which means it is not fire preventative. If you burn this, it'll put out toxic smoke. So they also had these in Teflon, which allowed you to place it in an air plenum. So part of our work as designers was to put this cable up in the ceiling of a building. We would look for return air vents. If the plenum airspace above the suspended ceiling had air vents, you couldn't use this PVC because it would kill the occupants during a fire. So you had to use the Teflon cable, which was about 5 times more expensive. And you can see that at every 2.5 meters, there's a black band around the cable. That black band is called an annular ring. And those annular rings are placed so that you don't have nodes too close to each other.
As the word ether implies, Ethernet was conceived from the beginning as a local area network based on a shared physical medium. This is also referred to as a bus topology. For a computer to connect, it would need to connect or tap into the shared cable. And we mean tap in the literal sense. Reed showed us what this process looked like.
So I've got this Ethernet cable with an annular ring. I'm supposed to tap it right there at the annular ring. The threaded center tap. So you put the annular ring exactly on the the center, and then you slide this cover over it, which has, you can see a compression fitting. So you slide that compression fitting, kind of a hard push, but you screw that down, and so you drill slowly. You're supposed to blow on it, which again is hard, wearing a hard hat and a face mask. So we put this tap with that part here and screw it down with this part of the tool.
Once the tap into the coax cable was done, a transceiver would convert the interface to AUI, or Attachment Unit Interface. An AUI cable would then connect the tap to the Ethernet card of a computer. And each end of the Thicknet coax cable is terminated by a 50 ohm resistor, which among other things helps prevent the Ethernet signals from each machine reflecting back when they reach the end of the cable. But creating the connectors for these terminators was involved.
You use some pretty monstrous tools in the Ethernet world. This thing is an Ethernet coax cutter. So I'm going to strip this cable. And you're doing this all on the top of a 40-foot man lift in the factory ceiling. Then this slides there. The crimp tool crimps that connector on. And this goes here, slides up tight. And then what do you use to crimp that? So this thing, you pump, and these jaws crimp that ferrule down to compress that ferrule. Done. All right, then we release the pressure. Makes a very satisfying noise. And now we have an end connector, and now we connect that to this 50 ohm terminator.
Well, that was easy. And on top of the practical difficulties, the road to standardize Ethernet was messy as well, but ultimately it resulted in the IEEE 802.3 standard. The Thicknet version of Ethernet was coined 10-base-5, with 10 indicating its speed of 10 megabits per second, base indicating a baseband signal as opposed to broadband, which in this case means carrying multiple services on a single cable, and 5 signifying its maximum length of 500 meters. That may sound like a lot, but remember these early installations were in large buildings and campuses, where spans of cable could easily exceed this distance. That's where a device called a repeater could be used, which can be thought of as a 2-port hub. Repeaters connected 2 spans of Thicknet cable, but also amplified and retimed the signals from each side of the network. This led to the infamous 5-4-3 rule, which states that in a path between any 2 nodes, there could be no more than 5 segments connected by 4 repeaters, of which only 3 could have connections to nodes. This led to a theoretical maximum length of 2,800 meters or 2.8 kilometers, and breaking this rule could lead to severe performance degradation. And the reason for this limitation? Collisions. The bus topology of early Ethernet meant that every computer or node on the network was effectively on the same cable. So when one node transmitted data, every single node on that network received it, regardless of whether it was the intended recipient or not. And the more nodes on the network, the higher chance of a collision, which is when 2 nodes attempt to transmit at the same time. If a collision did occur, a jammed signal was sent by the node that detected it, and nodes would then wait a small, random amount of time before trying again. And this is what limited the maximum network length to 2,800 meters, as signals needed to travel between the furthest devices within a specific amount of time to be able to detect collisions effectively. These inherent limitations in Ethernet led to the formation of the Broadband Project at DEC headquarters in Maynard, Massachusetts in the US. While their initial mission was to investigate interconnecting baseband Ethernet and broadband products like cable television, the group identified 3 environments which their solution would need to address, and it quickly became apparent their main goal would be to find a way to extend the physical length of the local area network. And one evening in 1983, before heading home for the day, Alan Kirby, the leader of the project, stopped by the office of Mark Kempf, a principal engineer and one of the best he had ever worked with, to discuss a potential solution. The next morning, Kempf came into work and presented the concept for a product that would be known as a bridge. This would be a device that connects two or more separate LANs transparently, just like a repeater, but that only exchanges traffic between the networks if needed. This technology was coined a store and forward switch. The bridge device would learn the MAC addresses of all the nodes on each network by listening for packets, and then storing the MAC addresses in memory. The bridge would then forward packets between the networks based on the destination MAC address. So in other words, packets from one network will not be transmitted across the bridge unless sent to a MAC address on the other network. This solution meant that each side of the bridge could be the maximum of 2,800 meters, doubling the size of the overall network to a massive 5.6 kilometers or nearly 3.5 miles, all over 10-base-5 cable. It was one thing to develop this concept in theory, but in practice, it would require serious engineering. The wire speed, or the maximum rate of packets in a 10 megabits per second LAN, was 15,000 packets per second. But the bridge would need to process double that in order to join the two networks together, meaning it would need to process 30,000 packets per second. This was near the limit of what the best CPUs on the market at the time could manage, and they ultimately chose the Motorola 68000. But Gordon Bell, who led the development of the VAX series of mini-computers, challenged Kirby and Kempf on the CPU, asking why the T11 CPU out of the venerable PDP-11 couldn't be used instead. The reality was that it was simply not fast enough for their requirements, and thankfully, Bell listened and the bridge project was approved. But even the 68K wasn't quite enough for one step of the bridging process. The network address lookup step was especially taxing. After a packet had been received, the bridge needed to look up the destination MAC address and make a decision whether to forward the packet over to the other network interface. But the source address also has to be looked up in case it isn't known by the bridge yet. None of the software solutions at the time were feasible, so over the span of several months, Kempf developed a programmable array logic that operated as a binary search engine. And coupled with dedicated RAM, the bridge could store up to 8,000 48-bit MAC addresses and look up an address in just 3.9 microseconds. And all of that sounds extremely impressive, but there was a looming problem. Both repeaters and this new bridge concept suffered from a potential network killer known as the loop. Loops in networks can be formed inadvertently due to layout mistakes or even intentionally to add redundancy to a network. If the conditions are right, a packet sent by a node can not only loop infinitely, but also proliferate in number as well. This can spell disaster for a network, and DEC manager Tony Locke wanted to solve this issue once and for all with the new bridge product. Locke dropped by the office of Radia Perlman, an architect at DEC, late on a Friday before leaving for a week-long vacation. Perlman wasn't a big fan of Layer 2 bridging to scale a network, preferring a Layer 3 solution instead, as she had previously worked on DECnet routing. But Perlman came up with an idea that very same night of transforming a loop-ridden topology into a tree, ensuring that every node was accessible without any loops. And over the next 2 days, she wrote a specification in enough detail that programmers like Bob Shelley had it working over the next month or so without needing to ask any questions. The new algorithm and protocol would be known as spanning tree, and it works through self-configuration. The protocol enables bridges to communicate with one another and choose a single bridge in the network to be designated as the root bridge. Each bridge then calculates the distance of the shortest path from themselves to the root bridge. This is known as the cost. This was later based on the speed of the interface in question, but during early Ethernet's 10 megabit days, it was based on the number of hops between a given bridge and the root bridge. From there, designated bridges for each network are determined, and a tree topology is formed. And the links that created the loops can actually be utilized as backups in case of a bridge failure, ensuring redundancy in the network. An entire video could be made on spanning tree protocol, as it has configurable parameters and its operation can be quite complex. And to be fair, loops could still be created by repeaters since they could not partake in the new protocol, but ultimately spanning tree solved the problem of loops with bridges. With Perlman's solution in hand, DEC was ready to unveil their new bridge. Dubbed the DEC LAN Bridge 100, it debuted in 1986 with a price of $8,000. And it may look simple from the outside, but this was the world's first bridge, and in fact, the world's first stored and forward switch. And we're lucky enough to have not one, but two LAN Bridge 100s in the lab. And we found this one at a place called Keyways. They specialize in all things DEC and beyond, and have a near unbelievable amount of hardware available at their warehouse. Mitch Miller, the owner of Keyways, was kind enough to loan us this LAN bridge when he heard about our plans to document its story. So we owe Mitch a huge thanks, and be sure to check out their website linked in the description below to see just how much DEC gear they have to offer. The design of the LAN bridge chassis is super minimal. There's nothing but the logo on the front of the unit, and for a device with just 2 ports, the LAN bridge is hefty and weighs 21 pounds. On the rear, we see the power input, dip switches, LED indicators, and the 2 AUI ports to bridge 2 LANs. The LEDs show activity on ports A and B, and there are indicators for power status, self-test status, and whether the bridge is online and operational. There is no power switch, so as soon as we plug it in, it powers up. We hear a fan and we see the LEDs come alive. The manual states that the unit does a 15-second self-test. Since we aren't building our own Thicknet network yet, we use AUI transceivers and hook up 2 separate networks. We see port A and B LEDs turn on, and the manual states that the bridge takes about 30 seconds to learn the MAC addresses present on each network, and to establish a spanning tree. We can't ping from one network to the other yet, so it must be in this phase. Sure enough, after about 30 seconds, we see the online LED illuminate, and we can now ping. The LAN bridge has successfully learned the MAC addresses of the nodes on both networks, and our traffic is being forwarded. It's actually working. We could also see the spanning tree protocol hello messages being broadcast from the LAN bridge, but the modern STP that our other network devices speak isn't compatible with the original DEC version. We ran a few iPerf tests to see what kind of performance we got, which admittedly wasn't great, but that's not the point. This is a 40-year-old device that is successfully bridging modern Ethernet networks, and it's doing so without any configuration. Just plug it in and go. Now that we know this one works, let's take a look at our other LAN bridge. This is a version called the Extended Remote Bridge, which was meant to link LANs separated by up to 3,000 meters using fiber optic cable that connects via Amphenol SMA 906 series connectors. Unfortunately, this one doesn't power on at all. We do see a small current draw, which then disappears. So let's take a look inside. The LAN bridge is well built with a total of 24 screws holding the metal lid on, and its design is well thought out for easy service. Inside, we first see the power supply with these monster primary side caps made by Mallory, along with the chunky secondary side caps. We removed the power supply as well as the fan tray to reveal the main board. It is covered in 7400 series and programmable array logic chips, along with the AMD Lance Ethernet controllers, and of course, its beating heart, the Motorola 68000 CPU. But we weren't satisfied with just leaving this one alone, so we've decided to try and restore it to like new condition. A LAN bridge definitely belongs in the Serial Port Museum. We're trying to reach 50,000 subscribers to help make this possible, so be sure to subscribe to the channel if you haven't yet to follow our progress over the coming months. With a plan to restore our LAN bridge, we can now take a step back and appreciate its incredible legacy. What started out as a way of solving a problem with Ethernet spawned an entirely new way of constructing a network. The LAN bridge was the first of its kind, introducing store and forward switching and a new device called a bridge. This groundbreaking tech was patented by its designer, Mark Kempf, but it was licensed out by DEC on a no-cost basis, enabling manufacturers to begin building bridges and switches of their own, which now power virtually every network on the planet. And it's thanks to people like Alan Kirby, Mark Kempf, Radia Perlman, and the rest of the DEC team that developed the LAN bridge that helped ensure Ethernet's success over its competitors in the 1980s. But that's not quite the end of the story. There was still one hurdle left for Ethernet to clear: the cable. Thanks for watching the Serial Port, and we'll see you next time.